just tell me the brief about yourself and what you want to understand more about the advanced embedded system. So during the our training process, we will focus on those core areas as well.
See, good morning. I'm Suraj Vanjishwaran. I have, around 6 years of experience in the industry as an embedded professional. I have
Okay.
worked on various embedded Linux Yocto distributions, standalone distributions. I have worked on microcontroller bare metal based projects,
Mm-hmm.
and also worked with Linux based projects.
Mm-hmm. Mm-hmm.
I have
Okay.
not worked much with device drivers, though I am interested in doing a course on the same.
Okay. So as
I
I will.
have done,
Mm-hmm.
have completed the CDAC where I have learned device drivers.
Mm-hmm. Okay. Okay, understood, Suraj. So we will start from starting as the syllabus has been already shared with you, right? So in
That's
the
correct.
first,
Yeah.
yeah, in the first, we will be discussing mostly on the introduction of the advanced embedded system. So mostly we will see the overview in this first
Mhm.
lecture, and we will also see the ARM architecture. So we will mostly focusing here for the ARM Cortex-M series of architecture. Okay.
Correct.
So
Correct.
both things we will be covering in this lecture. Okay.
Sure.
So let me start here. Just wait for a second. I will share my screen. My screen is visible, Suraj, right?
Yeah. Yeah.
Okay. So before starting to the ARM Cortex and these things, we will see how the embedded system evaluation has been done. Okay.
Hmm.
So give me 1 second. I will move this thing. Uh, okay. Yeah, that's fine. So mostly if you, because you already have some experience on that. So mostly in 1940s and 50s, how the embedded system would look like, just like a calculator. Okay, so we just use some of the controller that would be mostly from AVR or maybe the x86 architecture. Okay, so we will be doing mostly basic things that would be for military purposes, or these things we were using embedded devices. That time we were not using embedded devices for the consumer electronics. Okay, then after
Yeah. Yeah.
that,
Yeah. I
yeah.
understand. Yeah. Yeah. Go ahead. Go ahead. Yeah.
Okay, so after that, mostly the microcontroller series has come, in which we were using that Cortex-M series, basically connecting the input output to the microcontroller, some interface we are connecting, and we are fetching the data, just like a calculator and these devices. Okay, then after that, we were mostly talking about the real-time operating system, right?
Mm-hmm.
So because we were mostly writing the code on a simple bare metal code, means you are just writing the code without any operating system. Okay, the
Right.
main benefit is that, like, you don't, that code density would not be complex. You just need to write the code, these things. You don't need to bother about the multi-threading, you don't need to bother about the multi-processing and these things, because the Cortex M series or these type of small microcontroller unit only has one core, and one core means that can only done one task at the time, right?
Pardon for interrupting you, but
Okay.
recent ARM Cortex V8 has multi-core. I know people working in NXT who share
Mhm.
this information wherein you are having multi-core architecture on ARM Cortex series.
Correct. Even Cortex M also has some series in which they are doing a dual core. Okay, so
Yes.
how these things is working, let me explain you here. Okay,
Yeah.
so if you are aware about nowadays, mostly we are using advanced smart metering system, and IoT is very popular these days, right?
Correct.
So what things are happening? Give me a second. I will erase these things and I will start a simple diagram here. So earlier we were having only one microcontroller unit. Okay, which will
Mhm.
handle everything, and you will do in the simple interface and these things. But right now in IoT devices, what you are doing some wireless communication also, so you need some RF. Okay,
Mhm.
so they have divided in the latest ARM Cortex M series of, like you were talking about NXP, right? There
Yeah.
is TI also has done that. If you will see that, maybe I will share it later.
Mm-hmm.
That one IC in which what they are doing, that has dual core microcontroller unit. Okay, so
Mm-hmm.
what they are doing is that one core would be taking care of the application part. Okay,
Mm-hmm. Mm-hmm.
and the one core would take care of the RF part.
Mm-hmm.
What does it means? Like whatever data you want it from in nodes, because the smart meter architecture or these type of IoT architecture, what it happens, like you might be having hundreds of thousands of node, okay,
Mm.
and they will be doing the communication with each other, okay. So
Right.
either they will be doing star topology, okay,
Mm-hmm.
or they will be doing mesh topology,
Yeah.
okay. But
Mm-hmm.
right now why we are not using star topology? Because there are so much limitation over there, because in star topology you need some gateway in, through that you do the communication. Just like in our scenario we have a routers, right?
Yeah, yeah.
And let us suppose right now if we are using 5 gigahertz router, what would happen? The range would be very less, right? You will get speed but range would be less. That is inversely proportional to each other, right?
Right.
So
It's a trade-off. Yeah.
yeah, so if that, because generally we were using the same topology, but even in Wi-Fi, if you will see right now we are using Wi-Fi mesh. So how Wi-Fi mesh would work? Let us suppose, one second. Let us suppose we have a one router here in my home, okay,
Mm-hmm.
and we have so many devices, maybe one in first floor, one in second floor, one in fourth floor somewhere, okay. Range would be limited, maybe this range it router can provide, okay. So how you will do the communication with this? Earlier what we were doing, we have to add some repeaters, right?
Mm-hmm. Correct.
So this data will fetch here, and the repeater will broadcast or will do the means that will extend the range of this router, okay. But
Right.
that will increase the cost, and if that is limited area, then you can add one repeater. But if you want to cover whole city, okay, you cannot put so much repeater because it will do the overall cost, increase the overall cost, right? And in
Mm.
embedded system, you make sure you have to made a product in which the cost or the whole deployment cost would be very less, okay. So rather than using the this topology, they are started using mesh topology, okay. So what now it is happening, if this is not able to connect with this router because the extender is not there, it will do the communication with your laptop, and with your laptop the data would get forwarded to this, okay. So this will increase the unlimited bandwidth,
Mm.
means the range it depends on the node. So this is will also act as extender, and here if another node would come, then this will do the communication, okay. So one real life scenario I will explain you. In London there is one street in which there are no mobile communication, okay,
Mm.
because the street is very dense, and in some of the area you will not get uh, the even the mobile networks, okay. So what was happening with the England government, that UK, like they were implementing that uh, satellite, or what should I say, some uh, all the home automation type, like they were putting some cameras, CCTV cameras, okay, some electric meters were there, okay, in the home, some water meter was there in the home. They want to connect, they want to fetch the data from water meter, electric meter, and
Pardon me 1 second. Some issues there at home. Just pardon me 1 second. Sorry.
okay, okay,
I'm really sorry.
no issues.
Pardon me, as there are aged people in my house, so they have some requirements at times. Yeah. Sorry.
Okay, okay, no issues.
Carry on. Carry on. So you were telling about London. You were giving an example where there is no mobile networks. Carry
Yeah,
on.
so what we have they have done is, because they were our clients, what they have done is, because they want to connect everything like water meters, electric meters, and also that CCTV cameras through the cloud, okay. But if there is no network, what one way is, you have to put some router, through wired connection, right? And then you can you can give the Wi-Fi, and these would get connected to the Wi-Fi, and they will send the data to the router, and router or the gateway will send the data to the cloud, right?
Mm,
But the issue was you cannot put these type of routers, because you are putting these router outside, so that are industrial routers, okay, so that are rugged routers, okay, which is different as the consumer electronics types of routers, okay. So it that one router would cost around something like what should I say, maybe 10 lakhs or more than that, okay.
mm, mm.
So if they will be putting these in every street, that cost would be huge. So what they have used is they have used the latest technology, that is Bison. Maybe you might have heard, but that is very latest. That
No.
is okay. So this is just like a Wi-Fi, okay,
Mhm.
but this mostly used for embedded systems, okay. So just like all the IoT devices, like low power devices,
Pardon me, you are at a stage where you are explaining to me that there are two cores in the present day Cortex-M devices. One handles the RF communication and one handles the application. This
correct,
is from where we branched off. I
correct,
think we went on a tangent. Yeah. That's why I
okay,
was trying to remind you. Yeah.
correct. And this, what I'm explaining you here, means this RF will take care, okay,
Mm.
that core will take care of this whole thing, this Wi-Fi stack, okay, just like
Okay.
a Wi-Fi stack, okay. And whatever you want to do, you want to fetch some application data, you want to fetch maybe meter reading, you want to do something, then this would take
Mm.
care of everything, okay. So
Okay.
this we have already seen it. Later we will more discuss about these things, okay. So we
Yeah,
will
sure.
move back where we were discussing about Cortex-M
Yeah.
and the real-time operating system and these evolution, okay. After that the Linux and these things would come, but that
Yeah.
is not more important. We will move forward to
Mm.
the our ARM Cortex, okay.
Yeah. So
So
basically, in bare metal system, you run the direct .bin files. You execute the binary files directly. You don't
correct,
need necessarily an extended ELF file is not necessary. Okay, this is my understanding. A direct binary file can be executed by the processor by fetching the individual instructions and their operands and sequentially executing them. I'm giving you a very simplified case. Pipelining is involved and other things are involved, I know. Still.
correct. Mhm. See, the thing is, let me open this diagram, okay, so you will get better understanding here, okay.
Mhm. Yeah, and I
Uh,
would also like a short brief on the reset handler.
Correct. We will do that in this lecture itself. We will discuss about this. But before doing how the reset sequence would happen in ARM microcontroller unit, and what will happen when interrupt would come for the ARM Cortex M4 or all ARM Cortex series of microcontroller unit, we will discuss about that. But before that, we will see how is the memory organization. Okay, then you will get better understanding how reset is happening. Okay,
Mhm.
so mostly every or maybe before that, I just want to cover one more thing, okay, that is the Cortex AMR. You might be already aware about that because you have already worked on ARM Cortex A series, right?
Yeah,
So do you know what is the difference between A and M?
A is general purpose, M is embedded specific. This is what is the abstract understanding.
Okay, and in the internal thing, do you think what is the difference between M and A? Means okay, this is we got it, that is general purpose, or this based on
Okay.
the architecture, if you have any
Yeah,
understanding. Mhm.
see, there is something called as MMU and MPU.
Correct,
MMU is a
correct,
memory management unit which is used in a full-fledged system.
correct.
Okay.
Mhm.
It is present in Cortex A, and MPU is present in a Cortex M system, which is a very restricted version of, it will not handle certain high-level virtual memory management and things like that. Okay,
Correct.
so that is one fundamental difference.
Yeah, so the main difference is MMU and MPU, and another difference is MCU will be containing all the things inside,
That
just
is,
like RAM, ROM, and
yeah,
these things, right?
it's an
In
SoC,
yeah,
system on chip. Yeah.
correct. So that is the main difference. So if we need to run the full-fledged, yes, we have to use Cortex A, because for running the Linux and these things, you need virtual memory. For that, you need a memory management unit. So in ARM Cortex M, we don't have at the moment. So we only use MPU because that MMU will create a overhead, and we don't want to use, because overhead sometimes would be not good for any real-time system. So if you are building any real-time system, that you will be using a MPU rather than using, sorry, MCU rather than using any SOCs. Okay. And
Mhm.
there is one more series, that is ARM Cortex R.
Jazzle. I think there is a Jazzle series.
Yes,
R is real time.
correct. So R, see, R also has a multiple cores, but the difference is that in Cortex A, all cores will be doing different tasks, right?
Mm-hmm.
Let us suppose you have a two cores, both cores will be doing different tasks. That is ARM Cortex A. M we have already seen, that is only single core. Two
Mm-hmm.
cores we have seen, that is for different purpose we have used.
Mm-hmm.
And in ARM Cortex R, it can have multiple cores. Okay. But what difference is that each core will be running same task. Okay. So mostly we use a hard real-time critical system, just like in aerospace engineering, in automotive industry, we use Cortex R series. Okay. In R series, what would happen? Both core will be running the same thing, and we will see the result is same or not. If the result is same for both, then we will uh, do the task. Otherwise, we will not do the task. Okay. And
Mm-hmm.
why we are doing this? Because maybe this core has some issue, and that would, the result would get different, right? So if
Mm-hmm.
both result is different, that means some issue is either in the hardware or in the code.
Mm-hmm.
So then we will not execute this. So mostly in hard real-time critical system we use, in automotive sometimes we use, in aerospace engineering also we use. Okay.
In automotive, like for example, if I'm building an OBD stack, I'm running a current task where I
Hmm.
am developing an OBD stack for STM32
Okay.
F407. So
Hmm.
I am taking an Arduino example and trying to rewrite the whole thing. That PID, the CAN modes, those fields are there. Just I need to read OBD data. So that
Hmm.
should be fairly simple.
For that, you can do it simply with Cortex M. You don't need Cortex R.
No,
Getting me?
I'm using STM32 F407. I'm not
Yeah.
putting
So
R there. Yeah.
yeah, so that is using, you are using Cortex M series, right?
Yeah, yeah.
Okay. What was your question? Can you repeat again? Sorry.
No, I was trying to port an OBD stack, OBD
Okay.
protocol stack to an
Hmm.
STM32 F407.
Okay.
So OBD basically sits on top of CAN or other lower layer protocols which get data from the ECU. This is my understanding. So OBD packet format is there. So you are supposed to interpret that which comes in from the OBD reader. Right?
Correct. Hmm.
Yeah. So is there any simple way I can do this? Because I don't have any direct reference except an Arduino code, which I'm trying to change it by understanding.
This I need to check, but mostly what I have seen, that OBD stack, if they are implementing in automotive, they are using ARTOSAR architecture. Okay.
Okay.
And in ARTOSAR, yes, you have a low level driver library which is separate from this OBD stack which you are saying. Okay.
That is the
So
CAN. Basically, CAN is
correct.
there
Yeah.
or something else will be there. Depends on what is the legacy
Interface.
protocol. Yeah.
Correct.
Legacy protocol. Yeah.
So mostly in automotive they will be using CAN,
Hmm.
because mostly all the ECUs, electronic control unit, which is there in the automotive, they will be doing the communication with the CAN. So yes, the lower level driver should be CAN, or some companies use LIN as well.
Yeah. Yeah. Heard of them too. Yes.
Yeah. So it depends which the communication protocol they are using to do the communication with the ECUs. So if they are using CAN, yes, the low level driver should be CAN. If they are using LIN, the low level driver should be LIN. Okay. Now, okay, we have seen that. Now we will discuss about this, because Cortex M is also in various category from M0 to M7. Okay.
Hmm.
So if you will, it depends what you want to build. Let us suppose you want to build in which you want a battery power device, and you want to make sure that battery will last more than 10 years, more than 15 years. Okay. Then you will be focusing on Cortex M0 and M0 Plus. Okay.
Hmm.
Because you won't need to do, maybe the real life example I can give, a small data you are sending, just like smart meter also. Okay. You might be using M0 plus as well if you are not doing so much task. Okay, so earlier in the smart meters, they were using Cortex M0 plus because smart meters you will be putting some battery also. But right now, because there are so many overhead, they are also implementing through real-time operating system, Tiny OS or some other free RTOS or VxWorks. Then they are using M3 and M4 also. You can
QNX
implement.
also will do it. QNX
Correct.
also will do, right? Yeah.
Correct. But mostly what they, because in if we will see the IoT, so they use some other language that is similar to C, but that is Nessie. Okay, so maybe you
Heard of that.
might have heard that.
Yeah, yeah, yeah. This
Yeah.
one I have heard. I
So
have done some work also. There was a tiny bootloader which was written on that. Yeah.
correct. So Nessie is just a networking C. So mostly syntax is like C, but yes, you have to create the module, attach the module, these things. Okay. And there is a little bit difference between M3 and M4. So let us suppose you are using something in which you want to
DSP. That is the only
DSP,
difference.
correct? Yeah, digital signal processing. So if you are connecting any audio devices and these devices, then you might need Cortex M4. Okay.
M4, yeah.
If you are
Both
not,
what you call thumb architecture, right? Both work on the thumb instruction set.
correct.
M3 and
Yeah.
M4.
So if you
And
will see the instruction set also, so this is the total thumb instruction set. Okay. So if you will see Cortex M0 plus, that will be having a little less instruction set architecture. If you will see M3 will be having that much. That also include M0. M4 will be having a DSP related instruction set as well. Okay. So if you want to use those instructions, then you will purchase M4. Otherwise, M3 is more than enough to do the all these
right,
things. Okay.
right.
And if you have to work on the floating point unit, you might purchase that M4, which
As
supports
an SPU.
FPU. Correct. So what they are doing, this is the mostly FPU insect architecture, so they just added these things. Okay, and this M7, they also has some extra instructions, extra architecture.
Right,
Okay.
right,
Yeah.
right. So we have got the ARM exception model. We have got Pendesk with different exceptions, hard fault. See,
Correct.
I would be very grateful if you can give me real-time experience in debugging those things.
We
Those
will
for
yeah,
it.
so what in the next lecture we will use one microcontroller. Okay, and what I will do, I will create purposefully a exception handle, and we will see what exception handle has been done. Okay, so
I also
that
have an STM32F407 with me, and I have what you call as setup for other embedded systems like a Raspberry Pi. I do have. So you can also suggest me some good assignments to work on.
sure. So maybe in the next lecture, what we will do, we will write a simple bare metal code using maybe STM32. I also have it. I will just check. So we will write a sample code. We will purposefully do the fault, and we will see which fault has been occurred. Is it hard fault? Is it some other fault? We will see that. Okay.
Yes, yes, sure.
So actually that everything has been mentioned in the reference manual. We can see that which hard fault has occurred. But yes, we will see with the example. So you will get the better understanding on that. Okay.
Yeah, and I have written a STM32 bootloader with FOTA over UART.
Okay.
I'm doing it on my own. It's my passion. I'm passionate about the field. Hence,
Okay.
so I am trying to do something over UART.
Okay. So one more thing I would suggest, if you are doing that much thing, maybe you are directly sending the binary, right?
Right. The Bluetooth thing is slow. It's very slow. I figure out now I'm going to use something called as an MCP 555 Bluetooth. This is done over UART, which
Hmm.
connects over the UART interface to the STM32. It will fetch from a remote location the binary file over Bluetooth and take this over UART, use IAP in application programming, and flash it in the appropriate partitions which have been created for the bootloader and FOTA, and then change the first you de-init every peripheral, then set the MSP, and then you jump to the what you call as application reset handler. This is the method I'm following right now.
Okay. And do you aware about this SREC file format?
I have heard of this, but I have not gone in detail. I have gone only in detail of ELF.
Why?
ELF,
Yeah, why I'm saying this, because you are using Bluetooth. Okay, and in Bluetooth sometimes packet loss happens, right?
okay.
Yeah, because we have developed one bootloader for one company. Okay, what we have faced last time, we were sending those binaries. Okay, and
Mm.
that time, because sometimes it happens if it got mismatch. Okay, because you have to put lots of encryption once you are, because see, prototype is a different thing. Once we are deployed something, we have to follow something, right? So the advantage of the SREC, I'm just telling you, is that you will get this in that format. Okay, so you will generate a binary file in srec format, and in which you can check everything, the checksum and these things. Okay, so the logic was, uh, if if you want me to explain the logic here, we can do that. Otherwise, maybe we will discuss this later. What do you suggest?
We can discuss this later.
Okay,
We will continue with the course. I just gave you an information as to what things I am into, so that
correct.
you can tailor, the type of lecture. While the portion will be the same, but yeah.
We will discuss, because FOTA is very popular nowadays, and we will also cover this thing, how the whole design would happen, and what are the things we can do to optimize the whole FOTA system.
Yeah, yeah. Speed
Okay,
up you have to do for
yeah,
that Bluetooth thing. Yes.
correct. Even we have, actually I have developed that whole FOTA system for one automotive company, that is an Indian startup, currently, like that has been already deployed, and they are sending that electric vehicles right now.
Mm.
Okay, so we were discussing about, okay, these things we have discussed. We will discuss about this, then we will discuss about reset sequence, and what will happen when interrupt would occur. What was those two questions you have asked, right? But
Reset and
before,
use. Yeah.
yeah, so before that we have to know this thing. Okay,
Yeah.
why? Because while reset would happen, we need to know from where the it will fetch the data. Okay, how the instruction would get
See, we
started,
have
right? Mhm.
basically a load store architecture. That
Correct.
means
Mhm.
everything will have to be stored in the registers by the
Correct.
ARM Cortex architecture. So any instruction is first loaded onto the registers and then executed.
Correct. So, uh, before that, okay, first we will discuss this organization, then we will see the reset sequence from where the power on reset would happen. Okay. So this will get give better clarity. Okay. So first thing is, if we will see any microcontroller unit, it will be having a different types of flash. You might be having a flash memory, also the SRAMs also. So some microcontroller would have two SRAM, some would be having more than two SRAM. It depends on the industry. Let us suppose in automotive industry, if they might need more SRAM, that some NXP also focuses, like some microcontroller would be focusing on automotive industry. Like if you will see their S32K series, that mostly focusing on the automotive industry. Okay, so this flash memory, why we use, we mostly put the application code, vector table, and the read only data here on the chip flash. Okay, you
Okay.
can put these datas on SRAM also, so it depends on the implementation. You can see the size, and if you want to put it like in some of the photo system, we make sure one backup uh, firmware should also be there. Let us suppose in the latest firmware some error is there, you have to make sure one backup firmware is there,
Copy
right?
fallback system, copy failsafe system, wherein that you first, when you download a new code, you will first check whether it executes completely. If it
Correct,
doesn't execute, you will start executing the old one. That is
correct,
what you are referring
correct,
to. Right?
correct. Yeah. So if you are storing the backup firmware also, for that reason also, you can put it in internal SRAM. Okay.
Okay.
Then this is a system memory, in which mostly, if I will talk about the STM microcontrollers, so they will store their bootloader in this system memory, which is a 30 KB. Okay.
Okay.
So by default, it will not execute from here. So if you will run any STM32F4 board, it will start from on chip flash mostly. Okay.
Right.
It
It
will
has
not,
a 0x008000 and its alias 0x200 address.
correct.
Right.
So, but if you will change the MCU pin in the reference manual, they have already mentioned that we
The
have
boot
to
pin.
set boot pin.
Yeah.
Based on that, you can run this bootloader as well. Okay.
Right.
Then you have seen many devices has some product ID, right? If you will fetch that, then product ID would come, and based on that, you can see that. So this is one-time programmable memory that is also available on the Cortex series of microcontroller unit, that you have to put this data, like let us suppose you want to put your device serial number or something, then you can put it here. Okay, this is optional byte, that is also for the one time programmable memory for the write protection, because if you are putting the serial number, you want to make sure that has not been rewritten by somewhere else. Okay, so you will make it as a read only. And this is a backup RAM of for 4 KB, also available for this STM32F446 series. What it, let us suppose you are doing something, you have already something on the RAM, you can put the copy in the backup RAM. Okay, and even the STM32 would got boot up or the system on reset would happen, this backup data would be there in backup RAM. So this backup RAM will be getting the backup from the any cell or any battery over there. Okay.
Pardon me, I'm sorry for interrupting. This
Mm-hmm.
OTP memory, how does it work? So you are going to flash some information like product ID or serial number. Okay.
Mm-hmm.
So this is read only, right? It will not change once it is programmed.
First time you can do it, and if you want to make it read only, there is the option bytes which you have to set. Okay, so first you will flash the data or the bytes which you want to put, like serial number of the product. After that, once you will set this byte, it will become read only. After that, even you will not able to change this thing.
So option bytes are necessary to be used in conjunctions with OTP. Are you saying this?
Correct. If you are not setting it as a read only memory, then OTP memory can be programmed.
Okay, because what I understood once from reading some STM32 secure boot articles is that this
Mhm.
write protection is used for protecting the bootloader from unauthorized changes by physically tampering.
Correct. That is a read-only memory which you are talking about, this system memory.
Yeah.
Okay. In OTP, this one-time programmable, that is a very small, it is in bytes in which you can put some string, some types of serial number of data. Even they have put some limitation how much length you can put on there. Okay.
Mhm,
And once you will set the bit of this, then this will not get uh, change. This will never get change.
mhm, mhm,
Okay.
mhm.
So, and what you were talking about, yes, this is a system memory in which the bootloader is there, that they have made it as a read-only memory. So
No,
you
no, no,
cannot.
no,
Hmm,
no, no. I'm talking from the point of view of security. For example, you have
hmm,
got a system secure which is running with secure boot. So why you use secure boot? To ensure that whatever updates that are coming into the system are validated and authentic. Let us say,
correct,
for example, I contact a man in the middle attack and send some, malicious photo.
correct,
But if
correct,
it downloads it, it will check the maybe ECDSA and RSA kind of first integrity check it will do. Then it will check the encryption, and then it will validate whether it is actually authorized or no. If it is not authorized, if it is not, the encryption keys don't match, then
hmm,
it will, not execute that. Rather, it will stop executing that particular photo.
correct. That is for photo scenario. Actually, this OTP memory has been flashed before production itself. So let us suppose I have a router in which I have, so I will put the OTP memory before production. User cannot read do this and anything, because we, after putting this, we will put it as a read only and write protection. Getting my point?
Yes, yes.
Okay, so this we have seen now. Okay, we will see how the reset would happen, because let us suppose we have a bootloader here, or we are not running bootloader right now, we are just, what we'll see, how if STM32F4, we have a microcontroller unit, and if we are putting a power on reset button, or we are just applying the power, what would happen? So actually this has been defined in the ARM architecture. Okay,
Mm,
and whenever we will be doing the power on reset, okay, so
mhm,
the processor reads the value stored at the address 0 cross 0000. Okay,
mhm, mhm,
but you might have seen here they have mentioned 0 cross 800000, right?
mhm.
But ARM architecture, they will read it from here. But how this is mapping has been done by aliasing, memory aliasing. Okay.
I know.
Yeah. So whatever data, so let us suppose it will try to read this 0 cross 0 0 0 something. It will fetch the same value from 0 cross 8 0
Mm,
0
I know. That is
0.
where I have put my bootloader. Yes.
Correct. Yeah. So once power on reset would happen, the value stored at this address, okay,
Mm,
this value, it gets saved in stack pointer,
right.
which you can say that main stack pointer, MSP.
MSP. Yes.
Okay. Then after that, because it will start fetching the data from 0 cross 0 0 4. That is the next instruction. Okay. Where the address of the reset handler would get stored.
Mm, 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 mm.
So what would happen in this reset handler? It does some system initialization, maybe because you might have written some startup code in which these things would be there. Okay, so it will do some system initialization and directly jump to the C program what you have written, or the main function of your code, and
Mm.
after that the whole function would get start executing. And now it will depends whether the execution code will start like from flash, from ROM, from SRAM. It depends on your boot pin what you have set. So this is the mostly the reset sequence for that. So first it will fetch it data from 0 cross 0 0, but in case of STM or these things, the flash start from 0 cross 08800 something. So it will set it from there. Okay. And how these things would get changed? Now see, every time ARM controller should start reading it from here, but whatever you have set. So if you have set flash region, it will because the STM already know from where that this on chip flash has been started, so it will map it to here. Okay, let us suppose you have changed it to the some other maybe SRAM, so maybe they will alias it to this 0 cross 2000 something.
How does aliasing work internally?
Aliasing works uh, in this memory aliasing, whatever this data you what they will do. Okay, let us suppose this is the whole data. uh, this start is 0 cross 0800 something. Okay,
Hmm.
but what you are trying to do, you are fetching this.
Hmm.
So in memory aliasing, they will map this whole thing to here.
How is the mapping achieved? For example, let me go to the very fundamental basics. Whenever
How?
we are going to execute an instruction, that
Mhm.
instruction is going to be present at an address. So we have to
Correct.
first fetch the instruction after the reset sequence has occurred. So when the reset sequence starts, you get
Mhm.
an address. When you press the button, there is an interrupt. It is a
Correct.
non-vectored interrupt which branches to a fixed address. Correct.
Correct. Correct.
So that in this case is 0x00. So
Correct.
here CPU will load whatever is present here onto the registers, and that will be null. How will it know to go to 0x8000?
Correct. So if you will see, the boot pin will tell which memory aliasing, how they are doing is using just offset value. Okay.
Okay.
So if let us suppose they have set the check the boot pins, and that is set that start would be running from the on flash. Okay, so they will start aliasing whatever it will come from here. They will do some operation in the offset, add it, and this would get aliasing here. So whatever data is there, it will be getting fetching from here. Okay,
So
so
any idea
that
what sort of operations, any particular manufacturer or OEM, if you have an experience with any
because
brand?
yeah, because that code mostly they don't share with us. Okay, and that is not available in the open source also. STM
No, no,
has.
steps will be there. Like I don't want the code. I want a sequence of steps. Maybe add offset with base address and then jump to the instruction. Something like that. I don't want the actual JMP, MOV things. I just
Okay,
want a flow. That's it. If somebody
the
asks,
generic, yeah, the generic flow is means maybe the better level. see, I will tell you, maybe I will also check this and I will tell you, okay. But the basic understanding how this is happening is, once the power on reset would happen, this will check this address. But as the every company is doing memory aliasing, what it will do, once you try to run fetch the data from this address, it will check, okay, this is set, it means they wants to fetch this value from here. So this would get replaced with 0 cross 0080, and mostly companies are doing with offset value, okay. So they will add something here, and this address would become this address, okay, because the same aliasing would be there above also. So if you want to read 0 cross 0000, it will read 800. If you are reading 0 cross 004, the same offset value will get added and it will become 0004, okay.
Mm.
But the low level, what you have asked, add and these things, how they are doing it, I need to check whether they have given some info over there. So maybe I will
Yes.
check the ARM sheet and
Yeah.
maybe I will tell you in the next lecture, okay, this thing.
Sure. Sure. Thank you so much. Yeah.
So, okay, we have seen this. Then yes, we have to see while interrupt would occur, what would happen, right?
Yes.
Now we have seen the how the sequence would be once the power on reset would happen.
Yeah.
Okay, so
Right.
let me open. Okay, so the interrupt would happen either with the interface or with the timer, right? Maybe let us suppose an example. We have set one like timer, and after the timer would get fired, that one interrupt would occur, okay.
Mm.
So what would happen, this timer would send some signal to NVIC, nested vector interrupt controller, okay.
Mm.
And this is our CPU, let us suppose, okay. Means NVIC is inside that, I'm just telling, after NVIC whatever part is there, this is there, okay, or the
Yeah.
main boss.
Yeah.
Okay, so what would happen, let us suppose timer we have set for 20 seconds. After 20 seconds it would get fired, so it will send some interrupt to the NVIC, okay,
Yes.
some signal to the NVIC.
Either level triggered or edge triggered, that signal will be
Correct, yeah, it
basically.
depends, yeah, it
Yeah.
depends on the
On the
circuit.
interface. Yeah.
Correct. And then what NVIC got the interrupt, what it will do, it will notify the CPU that some interrupt has been occurred, and along with the port number, because you know this nested vector interrupt controller will take care of which port number would get occurred, because based on that the CPU will start executing that thing from the reset handler, right?
Yeah. Yeah.
So what then CPU what will do, maybe CPU is currently doing some task,
Yeah.
it might be possible because CPU will not be free every time.
Yeah. Then you'll have to
So
do context switching and so many things
correct,
that, yeah,
yeah, so what in context switching we will do,
push
maybe
onto
we,
the stack,
yeah,
push the
all the
old
stack
stack
old
background,
register, correct,
yeah,
so
onto
we
the
will
stack
pushed
pointing.
it,
Yeah.
yeah, pushed it,
Mm.
and whatever port number they have provided, okay,
Mm.
based on that there should be a vector table which has been stored, okay. And
Mm.
in vector table we will be having the reset handler. Let us suppose that this timer one interrupt will occur, so this vector table will get the data of the address, starting address of the handler, what you
Mm.
have written, or the interrupt service routine, okay. So let
Mm.
us suppose this timer handler is there, okay. So we got this data, CPU will stack all the current task registers, all the value, and start executing this handler, because it got the data. Then it will load it to the program counter, because this data it will load, because this will be having the base address of the starting address of the timer handler, and
Mm.
timer handler would get executed. And once it will get executed, it will go back and start pushing, or what we'll say, push it all this stack to there, and it will start executing what it was doing.
Depends. If it gets another interrupt, it will do something called as tail chaining. In
Correct,
that case, it will not do the push pop operations. It will continue execution in the privileged mode itself, that is the supervisor mode itself. In
correct,
case of ARM, we have got thread mode and handler mode.
correct.
So there is always a confusion for me, which is supervisor and which is ordinary. Which is ARM, thread mode is supervisor or handler mode is supervisor in case of ARM.
See, thread mode, uh, we will discuss about this, but one more thing, what you are saying now, thumb and this architecture, right? So
That is
one
thumb instruction and ARM instruction. ARM
correct.
instruction was now removed. Now it is all thumb only. It is a
Yeah,
condensed
because thumb
architecture.
2, yeah, thumb 2
Yeah,
is combination of both.
yeah, yeah. But it is a condensed architecture, and that old ARM 32 architecture has been obsolete. It is deprecated now, from what I understand. There was a TDMI controller which I used to use previously, which used to work on both thumb and ARM.
Correct.
Hmm.
Earlier, like if you will see ARM 7 TDMI series was there,
Yeah,
that was using means they will either use ARM or thumb. So you need to be change this thing, okay? But
yeah.
in the latest after ARM 7 TDMI, whatever they have put that Cortex M3 and these, in which they were using this thumb 2 architecture, okay?
And at that time, as a student, I was pretty disappointed.
But yes, but actually that would make our life easier,
I know
what
that.
I would say.
I know that.
Okay.
Just sharing.
So, okay, so this we have seen how this interrupt would occur when, okay, when these things would happen. Okay, then one more thing we will see. Okay, the maybe the registers and these things you might already aware how many register we have.
I can just look it up. I know I have done it multiple times. Actually, part of my preparation since long. I
Mhm.
have been going through all that multiple times, but I have forgotten now.
Okay,
We have got
maybe yeah,
register banks. Just
yeah,
have a register banks. We have got different.
correct.
Yeah.
Because mostly, see, if if we want to understand any CPU architecture, okay,
Hmm. We
what
should know
is
the
my fundamental is we have to see the ISA, okay,
yeah, instruction set architecture, right?
yeah, then the model,
Yeah, programmer's model,
correct, then the exception model,
exception model, right?
then the memory model what we have discussed,
Yeah,
right,
right.
and the last is the debug model.
Debug model, yes.
Based on my experience, if you have done this, then maybe means for any architecture, in my opinion you are the expert if you know this all these things.
Okay.
And in ARM Cortex M class, if you will discuss, mostly everything is a game of 21 register.
Hmm.
And each is 32-bit register because you know that is 32-bit microcontroller unit.
Hmm.
So in 21 register, first is, one second, I will increase the font. So one would come from R0 to R12 that you already might be aware that is general purpose.
Right.
So general purpose means mostly we will be using this for storing the data or intermediate values or any function argument, these type of things we will be putting from here. Okay.
Hmm.
Then there after general purpose, that is a stack pointer register. We use this that we can say as R13.
Hmm.
Then link register will also come into the picture.
That is when you're returning from a interrupt or what you call
Correct.
some
Mhm.
return address is stored there, right?
So it always stores the return address of a function call. So it will help CPU where they want to return to the appropriate instruction after the function call is get completed. Then this link register will come into the picture.
Yeah.
And program counter, you also aware like
That will
the pro,
keep
yeah,
track of the current instruction being executed, right?
correct. Where the current execution is there, it
Yeah.
will pointing to there. Then there is PSR,
Program status
program
register.
status
I know.
register, right?
So operation results, ANDing, NANDing, conditional
Correct.
faults, all those things are contained in that register.
Yeah, even the
Where you
state,
can prepare this as constant, static, volatile pointer, and then you can use a variable to read from this.
correct, correct. So everything like from status, from the conditional code flags, interrupt control bits, or the interrupt control handling, these things would be there in the status register, program status register.
Right.
Base, similar to that, there is also a control register
Hmm.
in which the
Modes,
control bits, yeah, like privilege modes, not privilege modes, stack selection, these things would be there in the control register.
control
Okay.
register. Both these
Then
are not accessible to be written. They are only
correct.
with the read-only
Readable,
registers.
yeah, read only register. You can only read that, you cannot
Yeah.
write those registers.
So basically, I have was asked in an interview where I was told that there is a practical use case where I can declare a variable static const volatile pointer. I said PSR and control register. I suppose my answers were right.
Correct, correct. The answer is right. Then after that, there is a special purpose register. You might have heard prime mask.
Ah, yeah, pre mask that
Correct,
priority interrupts are there. Na? Nice
correct.
priority they are specified
Yeah,
over.
which one you will execute uh,
Yeah,
these things. And if fault is occurred, that is also fault mask.
fault mask.
Similar to the, sorry,
Hard fault, and then many other.
correct.
Hard fault is very generic.
Yeah. And then last is, as per my understanding, was
Base pre.
base.
Base
Yeah.
pre.
So
Yeah.
that is base priority mask. Mostly it is used for a threshold for interrupt priority.
Can
Like,
I take a screenshot of this? I mean, this is well neatly drawn. I'll keep it for my reference purpose. Hold on.
okay,
That small one. Hold on.
yeah.
This is neat. Thank you.
And even the SP, you might be aware, is some two types like MSP and PSP.
Yeah, program stack pointer and main stack pointer. Right.
Correct. Even the PSR is also is APSR, IPSR, or EPSR. So APSR is application program status register. IPSR is interrupt program status register. So give me 1 second.
Yeah.
Maybe I will make one more here.
Yeah.
And SP would be in MSP and PSP. We were discussing about PSR. So PSR is also in APSR, IPSR, EPSR. So,
Mm,
so application, interrupt, or execution. And I think, yes, that is it
mm.
in the register programmable.
It's a
And
practical part.
one more thing people ask in the interview,
Mm,
let us suppose you are providing some parameter here like function, and we are passing some parameter like A,
mm,
B,
mm,
C,
mm,
or D.
mm.
So that is a very generic question they ask, like how this will get passed to the functions
Through the stack.
uh, through the stack. But this is not totally correct. R0, R1, and R2 is used, means if you are sending only three parameters, okay,
Mm.
it will go through these registers only, okay.
Okay.
If we are sending more than three parameters, it will go through stack, okay. So these three will go through register, and after that anything extra parameter you are giving, it will go through the stack. So
This is
once
got
we,
to do with something. Ha, yeah, yeah. Fine, fine, fine. Go on. Yeah.
yeah, so this because they have registered, let us suppose uh, three register they are using for passing the parameter. If extra you are using, that will go to the stack. And in embedded system, we most careful about the stack. It should not
Right.
get a stack overflow, okay.
Right. Right.
So while we were writing any real-time types of code, we make sure we are not sending more than three parameters. If we have to, then there is no choice. But if we have a choice, we will try to make a function which will be having a three parameter or less than three parameters.
I had
Okay.
once sent an entire structure in as a return. I had wrapped it
Mhm.
in C programming. It was an Yocto based system. I was
Okay.
yeah. I wrapped that entire structure as a there is a way to wrap it and then use it as a return type.
Okay. Okay.
It was
Can you
dangerous.
repeat again? I did not get it.
We cannot return. We cannot have a function struct. Uh, what you call struct add. Can you? You can't.
No, no.
Uh,
Yeah.
So there is a workaround wherein you can wrap a structure inside another return type like an object.
Okay.
Yeah. In C++, we can do that, right?
Correct. Yeah. C++
And
we can do that.
return that.
Mhm.
But that is
Yeah, that is
dangerously placed, which can result a problem if the size of that variable dynamically changes. See, in C++, you do this new and delete, right?
Correct.
So suppose the stack instance you are dealing with has a large amount of data, and you return it, your stack can crash if that
Correct.
system is a very simple system.
Yeah, even C++, they have that concepts they have made is very clear, like that even if you are using that pointer concept, that unique and shared pointer, that is
Yeah,
also very
that is
good,
smart
means
pointer.
yeah,
That is
a
smart
smart
pointer.
pointer, right? So they will make sure if there you are pointing to any object, that's okay. If you are not pointing, they will release it automatically. You don't need to do any memory management thing.
Mhm.
But the thing is, that thing will not give you much hold about the programming. Means if you have this much, if you can write all the low level things, you don't need to bother about these things, because in C++ so many things you can't do, but in C, yes, we can do that.
There is flexibility. I know this is
Yeah,
a low level language, which is it can work as more flexible control you get in pointers especially. Yeah.
correct. So what we will do, this thing also we will see
Mhm.
how this parameterize, as I told you, because now you can say how I can believe you, right? This
Mhm.
thing is happening.
Mhm.
So maybe in the next lecture on Sunday, we will see, I will write a program in which we will pass these parameter, and we will see at which register it is getting stored, whether it is going through stack or whether it is going through R0, R1. Then we will be having a proof. Okay.
So which
Then
which programming ID are you using? I am using STM32 Cube ID. It is there
see,
ready-made with it.
okay, then we will use STM32 as well, because
Cube
I have,
ID.
yeah, I
Cube
have
ID
that.
setup is there with you, right? And it's there with me also. That's not a problem. It is
Okay,
ready. Cube
because
ID, which is
I have
converted.
so many.
Yeah.
I have S32 also, because of that we will use for an XP.
Ah,
Key also I use, and okay, STM also I have. I need to just check. So we can use that. Yeah, I have that. So maybe we will use that. I will write a program and I will show you how this.
and
Uh,
and one more thing you have to show me. Suppose I have two programs. One is the bootloader, other is the application. I want to debug both. Let us say application is not hitting properly. I want to debug it. How can I run a debug session over a binary file for both? They are both flashed in different memory locations. I want to debug both.
okay, that actually for that reason they are, because in industry what we do for this, we have you heard about that IAR system? That is also a ID. I don't
Yeah,
have
in
it.
my
Yeah,
AR I have used this. I have used it. It is
yeah,
a paid one actually, so
correct.
no
Yeah,
need.
that actually providing, because that is a paid one, that provides something in which if this thing is occurring, you can simply check it with their Windows system, what
If
they
it is
have.
not available, what we can do?
Yeah,
There is an
maybe. Yeah.
option.
Okay. So you are saying one program is a bootloader and you have application firmware, right?
Both
And
are
you.
flashed in different memory locations as required, and you have to debug the both of them. Like getting it now. Yeah, you have got this is in the bin format. It is flashed in bin format. It is not an ELF file now. So how
Okay.
will you want to check whether it is hitting the application program properly during the debug session? How will I do this?
Okay. So, okay, I got your question. Bootloader and application program is there. One question is, all these things are on-chip flash or different one?
They are on the flash memory of STM32. Like I will say 0x8000 is the address for bootloader. Then you
Okay.
have got 32 KB is the allocated address for the bootloader. Then
Hmm.
at 0x80440000, you have got the application program reset handler.
Hmm.
Okay. Now I want to say run my debug session such that I am
Hmm.
not using the cube ID to flash. I am using it, flashing it using STM32 cube programmer. Okay.
Okay. Hmm.
Now, how will I run my debug session? How will I start my debug session to debug both the application, bootloader and application simultaneously?
Okay. Okay. So this scenario also I will check and we will discuss this. And also, so three things we will discuss it tomorrow along with our ongoing lectures.
Mhm.
First thing is this parameters.
Yeah.
Second thing, what you have mentioned, how we will check whether the hard fault and these things would get occurred using this
Mhm.
STM32 ID. That
Mhm.
is the second thing. And third thing, what you have mentioned, this bootloader and application session is there, and how you will debug it with the binary file. Okay.
Right.
So maybe if I will get time, I will try to check it and then I will tell you this thing also, third thing. Okay.
Sure, sure, sure. Fair enough. Yeah.
Okay,
I need
then
this actually. It's very important for me, this particular last problem which I stated.
yeah.
It
Okay.
is a part of an ongoing project which they are asking us to find out how this can be done on a Nordic semiconductor NRF52. But it is, if you teach me the same concept now, I will be
Mhm.
able to map it. That should
Correct.
not be a problem, right?
Correct. Okay. Okay, then I think if you have any other queries, we can discuss. Otherwise, we can close the call. We can meet tomorrow at 9.
So
Is
it's
it
a
fine?
daily 1 hour session, is it?
Yeah, yeah. Is it daily 1 hour session? Because I already have a corporate training on IBM from 10:30.
Okay.
So yeah, we have put one
So
hour
it's a
session.
40 hour is the total duration of the course, right?
40 hours. I need to check with the team because what we